In this video, we are going to look at differentiation by first principles. We can see that this diagram here has a lot of variables, and it may be quite confusing to kind of unpack and decipher immediately. But we will draw this back to the very basic principles that differentiation is essentially finding the gradient between 2 points, y2 minus y1 over x2 minus x1. So what we are doing is we are finding the gradient of this line between 2 points, P and Q. With the coordinate of P, we can see that this is something that we are kind of familiar with, or still developing an understanding for. That this is the coordinate of x and y. So why, therefore, is it called x comma f of x? Because this coordinate here is on this line of f of x equals x squared. So this is the example of our function here of f of x equals x squared. So essentially the y value is x squared. But instead of saying x squared, we can say, instead of saying the y value here, we can say f of x instead. It has the same effect. So it doesn't matter what our graph is. It could be a cubic, it could be a quartic. So as long as we take the y value, which is f of x. Now we can see here that Q is the point in question, where x, our original x here, spot the difference. It's been added by h, which is a horizontal value. So what does h actually look like? H is the distance from our first point up to the value of our second point, which is roughly here. So we've added on a h onto our original x value. Therefore, our second point here is x plus h, which is this x plus h here. So if our x value in this coordinate here is x plus h, how then do we find our y value? To find our y value, we substitute our x plus h into our original f of x, and therefore we will end up with f of x plus h, because we substitute the x value in. It's no longer x, it's now x plus h. That is our y value. So since y is equal to f of x plus h, we end up with this here. So the way that we write our coordinate, the x value of our second coordinate is x plus h, and the y value of our second coordinate, q, is f of x plus h. We are now going to use these two coordinates to calculate our gradient. So, if the coordinates of P and Q are these two, respectively, then the gradient of the chord PQ, my apologies here, it should be MPQ. I'll make a correction here in the notation. M, and the subscript is PQ, the gradient of the line PQ, not just the capital PQ. We know that we have x1, we have y1, we have x2, we have y2. we are calculating the gradients as we have written up here. So let's do a side-by-side comparison here. y2 is our f of x plus h. y1 is our f of x, which we substituted in. x2 is our x plus h, which we substituted down below. And x1 is our original x. Again, you can see the structural framework here of finding the gradient with the vinculum or the divided line and our two minuses in between each term. The reason why it looks like this final form here is because the x's, the x minus x, cancels out and we are left over with a h. So, we know how to find the gradient between two random points. But the idea of differentiation means that we are finding the gradient at one single point, which is the line of a tangent. So how do we find the gradient at a single point? The thing is, we see that these 2 points are very far apart from each other. If we want to get to a line closer to like a line as such, I will draw in a tangent line as best I can at this point P. Essentially, I just want that line touching just once. If I want this pink line to get closer to this red line, what happens if I move these 2 points closer? If I move this point Q closer to, let's say, around here, then we can see that our point is getting closer to the red line. You can see this is our point Q. If we move our point even closer, like such, let's move our green point, our point Q, over to here. This means that the lines going through would look like that. It's getting even closer to the red line. So what do you notice about the points? They are getting closer and closer. What does that mean about our value of h? What's our horizontal distance between the 2 points? They are getting smaller and smaller. So if we want it to be this green line, to be super accurate and super close to this red line, what does that mean about our h value? It needs to get closer and closer and closer, so close to each other that essentially our green line and our original point P are super close to each other that they become essentially one. So what does that mean about our h value? It means our h value is super small. So small that we say that h is approaching 0. And this is where we reintroduce the concept of limits. This is the gradient between 2 points that are far away. And when we say that h is approaching 0, we are bringing these 2 points super close together. I will write that down. This is the gradient between 2 points that are far apart. We also had a name for this. We called this the average rate of change. However, when we find the gradients at a single point, we are bringing the close. It's still the same calculation, except this time we're bringing the points super close to each other. This is the gradient at a single point, which is essentially 2 points that are super close to each other. We call this, therefore, what we call the instantaneous, at a single instant rate of change, which is synonymous with the topic that we are currently learning, which is the derivative. Differentiation, derivative, same. So this is the theory behind differentiation by first principles. And I will end the example here before we move on to calculating differentiation by first principles to some examples. Don't forget to pause and rewind if you want to rewatch how this concept is particularly explained at any point.